Hi, I want to welcome you back to more regular events, but still I have my ball in here, so if we're going to need it, we're going to use it. But let's look at the problem of finding maximum of three-dimensional functions now in more traditional way. Okay, we already had some hints. We definitely need to use partial derivatives for that. And look, if our function is z equals f of xy, then of course we can calculate two partial derivatives, dz dx, or fx for short, or dz dy, or fy. Okay, and look, now what I'm going to try to demonstrate to you is going to be how those derivatives work. Okay, so I'm going to start with derivative fx, which I'm going to denote tx. To be consistent with your textbook, this is how it's denoted, probably from the word tangent. Because look, what I'm going to do now is I'm going to draw a line that is tangent to our sphere. Remember, our sphere, we want to find maximum, of course, for this sphere. Right? And as it was with the ball, this, of course, is empty inside. We do not actually see this part. This is why I draw it with a dashed line. So we see only this. Right? It's empty inside, and we are looking for top of it. So if we are going to use derivative to actually find it, how are we approaching the problem? Look, if I'm looking for if I'm finding a derivative, as we said, we want to find a place where this derivative is equal to 0. So we will be drawing the lines that are parallel to the x-axis, right? So in this, in here, we can find infinite amount of lines like that. When we get a function of just one variable, so two-dimensional function, for each local maximum or minimum, we could just find one. Now we can find infinite number of them. And look, if I'm, for example, going to place a line like that over here, I'm going to call it tx1. Okay, look what would it do? It would find me a maximum from some perspective, right? It would be, of course, here is the top. We would get simply a part from perspective of x-axis. We would see that this point is actually at the top, but only in this specific location. Why? Look, it's like this point would be somewhere over here, right? If you look just from this perspective, you can place a line that is tangent to this ball, right? And is completely horizontal. But now, if we look from the other perspective, so from perspective of y-axis, we could easily see that if we move to the right, if we move in this case from perspective of y-axis, it would be like up front, we can get higher. And look, we can find actually, as we said, infinite amount of lines that would be tangent to this sphere. Each of them would be associated with this parabolic shape inverted parabolic shape. But of course, we are not on the top. And look, we can go on like this until we actually arrive on the top. I'm going to call it TH max. Okay, now we can perform exactly the same exercise from perspective of y-axis. Look, imagine that I'm taking this coordinate space, that it's like this, and I'm rotating it like that until we are in this position. So look, now we're having the y-axis in front of us. Okay, and look, again, I can now calculate partial derivative with respect to y and obtain a line that goes like this. Ty, y. And look, we would have encountered exactly the same problem. We would be able to find, okay, not a very nice one, but I hope you know where I'm going with this. We would be able to find a place where the slope of this line, from perspective of y-axis, is equal to 0. And look, we could find a lot of places like that. But again, none of them is at the top. And look, of course, at some point we will arrive at the top. And what is so characteristic about this point? Look, from perspective, if I would like to draw now a line through the same point from perspective of x-axis, what would I have to do? This line would be going, parallel line, would be going like this. It would went through this point, and then it would cut through our sphere. Now, I could do the same thing over here. Imagine that those are actually perfectly parallel. And again, I would go through here, but the line would be cutting through our sphere. So look, of course, it means that from perspective of y-axis, over here, I've got a line that is parallel and has a 0 slope. But look, now, if I would get the same line from perspective of y-axis, look, it would be, okay, here we have y-axis, here we have x-axis, right? And now, look, what is happening over here? Now, if this line goes over here, actually, they are either intersecting behind the ball, or if I want this line to go through this point, you know, it would have to go through the ball inside. So we clearly see that these points over here are not very well in case of finding maximum. They find some point that is the highest from perspective of one axis, but it's not the point where that is highest everywhere. And look, I could do exactly the same reasoning performed over, I could have exactly the same reasoning performed over here. Look, I could draw a line, let me just do one, with respect to y-axis, but then the line would be cutting through our sphere. So, what do we need to do? Look, in all of these cases, I was requiring dz dx or fx to be equal to 0. And then I was trying to address another point, to find another line that goes through the point where this intersects with our sphere. And I was doing the same here from perspective of derivative of y. But look, this should actually lead us to very, very easy and logical conclusion. That in order to have maximum, what we need actually is for both of these derivatives to be equal to 0 at the same time. Because look, over here, it would mean we would have a line that goes like this. And this line is also, look, you need to, I'm going to show you on the ball in a second. Like, those two lines are tangent to this sphere only in one place, at the top. And the same situation is actually over here. If I would draw now T, Y, M, so then we would have two lines tangent to the sphere and just one at the same place. And look, actually, this is the same sphere, just seen from two different perspectives. So look, from this, we get that the first order condition, okay, let me now erase that. If we have 3D function given by z equals f of xy, then first order condition requires us for both first partial derivatives to be equal to 0 at that particular point. Okay, now let me just demonstrate this with the ball again. Look, if we have one line that is, let's just say, parallel to x-axis now, that is tangent, and at the same time the second line that is parallel to y-axis, right? Then this means that they are both parallel, they are both tangent at just one spot. And look, what they actually create is a sphere, is a plane. Look, in this plane, it should be touching our ball in just one place. So look, we would have a plane that is perfectly flat, and it catches the ball in just one place. And look, this is the entire idea behind finding maximum and minimum finding maximum or minimum of three-dimensional functions. So look, first order condition is very simple here. We just take partial derivatives, we equalize them with 0, and we find for values of x and y for which those conditions are met. Okay, so now that we've got first order condition, of course, we should move on to second order condition. Okay, so how do we gonna approach this? Look, here I will not give you the full derivation like we did with everything here basically. Well, this derivation would require us to go through something called quadratic forms. But I'm gonna give you some intuition behind it, and in the link to the video I will write where exactly you can find information on how it is done. But for a second, let's go back to the 2D look. So, look, we've got, of course, axes x and y and z. And let's just say that using the first order condition, we found maximum. Now, how would this look from above? Look, from above, it would look something like this. But here we have some y-axis, here we have some x-axis, and here is our sphere. This is what we see. Look, basically, now we've got this. So, we know now, using the first order condition, that let's just say that this point let's note it as x0, y0 is our maximum. Okay, so in these circumstances, we know already that this is a maximum, but how can we be sure that this actually is a maximum? Imagine that you're standing on the top of a hill, or on the top of a ball. What is specific about being on the top of the hill? The specific thing is that it doesn't matter in which direction you're going to move, you will always go down. And look, this is the entire idea behind second order condition for maximum. Now, here we can move in 4 different directions, basically away. Okay, and what are those directions? Look, we can move from x0 to the right? So we will have here dx, that is positive. We can also move from this point to the left, so we can have dx, that is negative. Then we can move on y up, so we will have dy, that is positive, or we can move on y down, which means that dy is negative. Look, these are our only 4 options. But look, those options here basically include moving here in this direction and moving here in this direction, moving here and moving here. Okay, but of course we can move on x's and on y's at the same time. So look what does this create, like a variety of possibilities. Look, because if we move over somewhere over here, we see that over here dx is positive and dy is positive. Now look what happens over here. Here y is getting bigger, so dy is positive, and but dx is negative because x is declining. Over here, x is still declining, but y is also declining. And finally, over here, dy is negative, and dx is positive. Okay, and look, here we see the different combinations of possibilities we can have when we move. Of course, look, I draw this here in a very big manner so we can see, But actually, remember that all those moves, all this movement I've been telling you about is just a slight movement away from this point by very, very small amount. And look, let's again see what happens when we are at the top of the ball. If we are at the top of the ball, it means that it doesn't matter in which direction I am moving, I should go down. But look, what should go down here? Not x, not y, z. So look, we should have a situation where when dz is always negative, right? Right. Look, because what does it mean? Look, if we are at the top, it doesn't matter in which direction I'm moving away from the top, I'm always going lower. Okay, but this is going to create a slight problem for us. Because look, before, when we were talking about, for example, differential condition for function of just one variable, the case was very easy. Look, because we get it like this, that if function is y equals f of x, then differential dy is equal to f prime of x dx. But now we have a function of two variables. So look, here we have a case like this. If x is changing, it influences y. Now our entire situation got slightly more complicated. Because now we have two variables, variable x and variable y, and each of them, through function f, is influencing another variable z. Now, if I want to know what is dz, I'm going to be also calculating differential. But this time, we're going to call it total differential. Okay, and look, how does the total differential look like? Look, now, change in z can come from two sources. First is change in x, and the second one is change in y. Now, how z is changing as x is changing, this is of course described by partial derivative dz dx. And how z is changing when y is changing is described by partial derivative dz dy. Or more simply put, we've got the dz is equal to fx dx plus fy dy. Right, let's use this notation because things are going to get slightly more complicated this time. Okay, but now, if we look only at this total differential, we will see that there is a problem right away. And where do we have this problem? Look, because here we have a case where dy and dx can be either positive or negative, or each of them can be of the different sign. So look, this right away creates a very problematic situation in terms of assessing the sign of dz, because dx could be positive or negative, dy could be positive or negative. So maybe there is another way of dealing with this problem. And look, actually, I'm not going to give you the details, I'm going to give you the gist. But it's going to happen just like in case of function of one variable through second differential. Second differential is, of course, a differential of the first differential. So this is a differential of fx dx plus fy dy. Okay, and look, here is when the situation is becoming very, very tricky. Look, let me just show you one simple thing. Look, if I'm differentiating those two expressions, calculating differentials follows the same rules as derivatives. So it's not a big problem. But look, so I can use the rule that sum of differentials is differential of the sum is sum of the differentials, right? So I can divide this into two separate expressions, and I can rewrite it a little bit differently as d fx dx plus d fy dy. Okay, and look, of course, this expression over here is a derivative of the function z equals fxy with respect to x. And the same here with respect to y. But look, if we have a function, for example, it doesn't really matter. Okay, if the function is z equals 14x squared times y to the power of 3, then look, fx, so derivative of z with respect to x, is equal to 28x times y cubed, and derivative fy is 42x squared y squared. So look what happens. Actually, derivative with respect to x is a function of both x and y. And derivative with respect to y is a function of both x and y. So we need to take this into consideration when we proceed with calculating a differential. Okay, so what we are getting out of this? So here we can differentiate this expression with respect to x and with respect to y. So we're going to get that out of this, that this is going to be fxx dx, right? Now we're differentiating this function with respect to x, and we're differentiating then this with respect to y, so we get fyx dy times dx. And look, now we need to repeat exactly the same steps for fy. So we are getting that this is fxy dy plus dx fyy dy times dy. Okay, and look, we can easily notice that based on Young's theorem, those two expressions are identical. So I'm going to write them from this point on both as fxy, right? Okay, now let's multiply all these things out, this whole thing out, and we get that this is fxx dx squared plus. And look, out of this, I'm going to have dy dx, and here also dx dy, which is the same. Those two are the same. So we are having here plus 2fxy dy and then dx dy. Okay, so it's nicer. And finally plus fyy dy squared. And look, this expression is the expression for the second differential. And the second differential of z, and because this expression is an expression for a second differential of z, we can actually use it to measure what is happening to z around the point where we have either maximum or minimum. And now, knowing this, we can actually formulate the second order condition. And look, we're going to do, in this case, just sufficient. A sufficient condition. We're not going to be dealing with more complicated cases, so this is enough. So we've got sufficient second order condition for either relative maximum and minimum. And now look, because we've introduced this expression, we know taking into consideration every possible dy and dx. Okay, now, why is that so important? Well, this is so important because going through the... okay, one more thing. Okay, let's start easy. So, now, if d squared, if we've got that d squared z is always negative, it means that this point is the top of the ball. Why? Because look, if I move from this point in any direction, I'm going lower. So this point, of course, must be a maximum. Now, on the other hand side, if d squared z is bigger than 0, what does it mean? Look, it means we are at the bottom of the ball, so we are in the minimum. Why? Because look, in any direction I walk from this, any direction I move inside this ball, I'm always getting higher. So this point must be a minimum. Okay, so now that we've got those, then what else can we say? Look, as I mentioned previously, we derive the specific condition, in this case, using quadratic forms, and I'm going to give you a description where exactly you can find very accessible and easy derivation in your book. But we're not going to do it because we would have to spend probably like 2 hours on it, and this is, let's just say, a little bit beside the point over here. So I'm just going to show you the result. As it turns out, that if we want to assess the sign of d squared z, we are only thing that we are going to need are those derivatives. Look, why is it like that? Because look, this is actually the thing that we wanted. Why? First, because we wanted to, and this is easy for us now to calculate partial derivatives. We know how to do it, right? And the second is that we want to know that this is either bigger or smaller than 0, regardless of what are the specific values of dx squared, of dx squared and dy squared. They are always positive, but for dx and dy. And look, in order to, so the device are we going to use over here is called a Hessian. And Hessian is a determinant of second derivatives. Okay, so how will this Hessian look like? Look, as the name suggests, a Hessian is made out of second derivatives. But to get second derivatives, what do we need to have first? Of course, first derivatives. Look, Hessian, we denote by H. But because it's a determinant, we also put it inside the two bars. Okay, and look, we're gonna find it using the similar technique I've been showing you actually for this reason when we were talking about partial derivatives. So look, imagine that we have no, not imagine. Here we have a determinant, and look, what do we do over here? Like here, let's just say that first row is associated with the partial derivative with respect to x, and the second one with respect to first derivative with respect to y. Now, each of them can be differentiated with respect to x and with respect to y. What will we get here? fxx. What will we get here? Let me write xy, because here we're also going to have fxy, and here derivative fyy. Look, of course, remember that those are Newton notations, and this means exactly the same as partial derivative of z with respect to xy, so dx squared, then here we have dz dx dy, d square z dx dy, and d square z dy squared. Okay, and look, we actually can calculate the value of this determinant once we know everything inside. And then, how does the maximum and minimum work? It turns out that if first, one more thing. Principal minors. I don't know if you remember those, but from our matrix algebra, but this over here is what we're going to call first principal minor of Hessian, or H1 for short. Look, if we want to find first principal minor, all we gotta do is to cut down the first part of the first square from the determinant. So actually, in this case, we can do this. We can find 2, because we can find either H1 or the second principal minor, or H2. Okay, and look, so H1 is simply, in this case, fxx, and H2 is this whole thing, so it's equal to fxx times fyy minus fxy squared. Because remember, this is a determinant, regular. But look, out of this we of course calculate the first principal minor and the second principal minor. We calculate out of the Hessian H1 and H2. And if it happens to be that H1 is lower than 0 and H2 is bigger than 0, we've got a maximum. Now, if it happens that h1 is bigger than 0 and h2 is lower than 0, we've got a maximum, a minimum, sorry. Now, but at the same time, you need to, oh my god, they are both need to be positive. Well, I'm sorry, it's really late, I'm very tired. If first principal minor, so this one, is smaller than 0, and the second one is bigger than 0, it is maximum. Now, if this one is, if h1 is bigger than 0, and the second one is bigger than 0 as well, this is a minimum. Look, if it would turn out that either of these, well, if h2 is smaller than 0, it would mean we have a saddle point. It means that this basically would mean over here that in some directions, when we go in some directions, we go up, and in some directions, we go down. Remember, saddle point looked kind of like this, and it is a counterpart of inflection point, but in three-dimensional, in case of three-dimensional functions. Okay, so summarize. If we want to find maximum or minimum of a three-dimensional function, we use first-order condition. We find where we calculate first derivatives and we equalize them both with 0 and we solve. Then, after we do so, we move to the second-order condition and we calculate the Hessian, which is the determinant of second derivatives. If it turns out that first principal minor of a Hessian, or h1, is smaller than 0, while h2 is bigger than 0, it is a maximum. If they are both positive, this is a minimum. Okay, so this is enough about the theory. In the next video, we're gonna do some examples that are gonna allow us how to use this rule in practice. Okay, thank you for your attention.